Simple harmonic motion, the pendulum. We have a simple pendulum shown here. There's a string of length L which is connected to the support. At the other end of the string is a mass M connected. When the mass M is slightly displaced to the right and let free, then it begins to oscillate. When the mass M is on the right side of the mean position, this is the mean position of this oscillation, then the restoring force is towards the origin. Likewise, when the mass M is to the left of the origin, the restoring force is to the right, towards the origin. So the restoring force is always directed towards the origin, which causes the simple harmonic motion. That's the first observation. So we draw the free body diagram of the mass M. The mass M is at this center. Its mg force, which is acting from the center of gravity, is always pointing downwards and constant in magnitude. The magnitude of mg does not change. The tension, however, changes slightly. Because theta is assumed to be a small angle, the T changes slightly. So on the body, the T is acting upward towards the support, as shown. We resolve T into horizontal and vertical components, which are respectively T sine theta and T cos theta as shown. These are our coordinate axis, the right-handed coordinate system, and the mean position of this oscillation is taken as the origin. The string length is given as L units. Now, in the y direction, if we write the equation of motion, we have T cos theta must equal mg, because there is no effective force in the y direction. And that's a consequence of the assumption that theta is small, so the oscillation itself is almost on a straight line, on a horizontal line. So that's what is implied when we assume that theta is small. Equivalently, we may assume that L is long enough. So in the x direction, we have T sine theta, the restoring force, which is causing the acceleration, is mx double dot. X is being measured from the origin, from the mean position, as shown here. Note that the minus sign is attached to the T sine theta because this is the restoring force and this is always directed towards the origin, whether x is positive or negative. Now we may apply the condition that theta is a small angle. Trigonometric approximations imply that cos theta may be approximated as 1 when theta is small, and sin theta may be approximated as theta when theta is small. Also, x is L theta when theta is small. It may be seen that sin theta is actually opposite side by hypotenuse. So since sin theta is theta, we have x is equal to L theta. So from equation 1, with the approximation, we have T equal to mg. And from equations 2 and 3, we have this equation, where we have substituted theta as x by L. It follows from equations 4 and 5, these two equations, that x double dot plus g by L equals 0. So this is the governing equation of the simple harmonic motion. Note that this equation is independent of m, even though the given mass has m units. The m explicitly does not enter the governing equation, which describes the harmonic motion. Also, as theta is small, we have x equal to L theta, like we said previously. It also follows from equation 3 that x dot is L theta dot and x double dot is L theta double dot. Using equations 3, 7, and 8, we may rewrite equation 6 entirely in terms of theta as theta double dot plus g by L theta equal to 0. So statements at equations 6 and 9, 6 is in terms of x, and theta is the variable in equation 9. Both of these equations are equivalent descriptions of the simple harmonic motion.